Hi, I'm Ravikumar Alluboyina, and I have Tushar Doshi sitting there. We work for Robin Systems. And let's talk about big data applications, and especially deploying big data applications on Docker and Kubernetes Platform. So the way we want to drive the talk is by presenting a problem statement, as in why is it difficult to deploy big data applications on Docker, and on top of that, Kubernetes. So we call ourselves Kubernetes ++. So we are based on Kubernetes Platform. So we wrap Kubernetes and provide value add. And we'll go into details on how we do that. And we are not joking, by the way. So we have production customers running load on Elasticsearch, Kafka, and Oracle. So we specialize in SQL, NoSQL, big data, and AML workloads. So we can run all these 4 types of workloads on Robin. Okay, let's jump in. So what's the big deal about the big data applications? So we took Hadoop as an example. Let's walk through the biggest problems. So some of them might seem trivial to you, but it's spilling the onion. Let's stay with me. Let's say you have 2 racks, and these big boxes are physical servers. Called the Unicity instances, but let's say the physical servers. And we have storage, which is Dash. Let's start with a very simple Hadoop deployment with 3 data nodes. Obviously, this is not a very good design. It's not fault tolerant. It's nothing, actually. You have 3 data nodes sitting on a single node. Your node is down, and everything is down. Obvious answer. Spread it out. So you make your compute fault tolerant. So what's the trick here? You have to make this, or you have to bring this concept called anti-affinity. So if you have services of the same kind acting as redundant components, you have to spread them out. So you offset the failures of the physical hardware that they're sitting on. This in itself is not enough. I jumped. I gave you the answer. So we have to make it fault tolerant, rack fault tolerant, which means you take one of these out and put it in a different rack. So this is the 2 reasons. One is to make the service itself rack fault tolerant. The other thing is when application writes, it can write to different racks. So we have to make the application location aware in terms of rack, lab, or data center, or the host. So that's the second point. Now comes the storage. So we are talking about virtualized platforms, both compute as well as storage. So we have no control on where the data blocks are actually coming from, the logical to physical mapping. And especially when multiple vendors are involved in creating a solution, one providing compute virtualization, the other providing storage virtualization, it is very, very difficult to map. They have to work in tandem to provide the desired result. So as you can see, obvious problem again, all 3 data nodes are deriving storage from node 1, and if that is compromised, HA is compromised. Solution, move it out. Somehow make the storage stack provide storage from 3 different physical servers and, of course, 2 racks. So we make the storage fault tolerant. So far we have talked about a very small, a significant part of Hadoop, which is your HDFS file system, the data nodes here. Let's move on. Hadoop is a platform. It's not just one application, right? So you have Zookeeper. The trick with Zookeeper is, note that in this diagram, Zookeeper is actually fault tolerant to both storage faults and compute faults. But what's missing here is you need latency. Zookeeper has to write as fast as possible to the storage. So in this diagram, you see that the compute is here, where it's deriving the storage from the other node. It's crisscrossing, actually. It's not a bad. It's not a good setup at all. Fix it. So you get it from the same host. In a way, what we are saying here is, if the component has built-in redundancy, and if it is keeping multiple copies, stick to the old philosophy where you have storage and compute affinity. Put the compute closer to storage, or vice versa. So far, so good, but Hadoop, as I said, is a platform. There's more than just data nodes and Zookeepers. There are components which are not protected by the core architecture itself. HDFS is protected. You have 3 copies. Zookeeper is protected. But there is Cloudera Manager in Cloudera distribution or Ambari server in Hotmost distribution. So essentially, it's a web server with some database backend. And who is protecting this? Nobody, right? It's not, the data is not sitting on HDFS. It's in MySQL. So again, this becomes a problem. If node 2 were to go down, your Cloudera Manager is compromised, which means you cannot orchestrate your Hadoop cluster. How do you protect this? So we replicate the storage, the MySQL storage, and the container itself is protected by Kubernetes or whatever is the orchestration engine. You just lift the container out and move to a different rack or a server. So we solved that problem as well. So what now? Unfortunately, there are too many such components in the entire Hadoop ecosystem. There are some which are self-protected by HDFS replication or Zookeeper replication. There are many components which are not. So you have to have that redundancy. And we need to find a platform which can offer all of this, which can protect all the components in the Hadoop platform. So these are the essential components that any orchestration system or any end-to-end solution that claims to support data-heavy application needs to have. They have to support different workload types. As I said, your traditional transactions logs in a database are latency sensitive. HDFS is throughput sensitive. There are different volume I/O characteristics. You need QoS settings, compute anti-affinity or affinity, storage affinity. Storage affinity is actually the biggest thing, I would say. Location awareness, availability for the components. So this part is essentially for running Hadoop or day 1 or day 0, your deployment. And after that, admins has to deal with growth. They have to scale out. But when you scale out, you still have to follow the same rules. You cannot violate the storage and compute affinity policies and all that. Even during failovers, you have to worry about affinity policies, otherwise your cluster is compromised. And there are snapshots and rollbacks and data protection by streaming the content out to cloud. Okay, so there is Kubernetes and there is Docker. It's a big deal, right? What we have seen is the biggest problems in that ecosystem is 48% relates to storage and 44% relates to networking. And there are 27 storage vendors and 21 network vendors. Why is it that deploying a big data application is still painful? So that question needs to be answered yet. I hope you got some idea on why is it so difficult to deploy Hadoop application. There are other challenges other than Kubernetes. We talked about Kubernetes and the problems, or Hadoop and the problems, right? Even in the container world, Docker container world, there are some problems. You have to virtualize your proc file system, sysfs file system. That's not enough. What we have seen is there are some library calls that are made, so you have to intercept those calls in order to present the right CPUs and memory values on the other devices to the containers. And these are some use cases. While working on different applications, we found that Kudu requires a contiguous CPU IDs. In the C group, you can define a comma-separated list of CPU IDs. You can have random numbers, but Kudu won't work with that. It has problems with that. And in some of the JVM applications, we have seen that they use system calls and figure out what's the total available memory. Even if we virtualize proc and sysfs, that wasn't helping. It says, I'm going to take all the 255 gigs of RAM that's available on the system, and that's going to cause problems. And in storage, the block I/O thing is particularly interesting. If you have a quality of service enforcement, it can be done per volume, on a per volume basis. Any containerized solution will allow you to do that. But if you talk about a data node, it is actually managing multiple volumes. It's not a single volume. So what we can do, or what we have realized, is that the QoS enforcement has to be done at a data node level, not just a single volume level. Because if you have to do it at per volume level, you have to set 10 each or 100K each. But what we want to do is, this data node cannot consume more than 200K items. So that's a problem with block IO. It's a management nightmare if you have to set block IOs for each and every volume. So why is this? In my opinion, when these applications are built, or even when they're getting built today, they are built for a setup which is like 5 years or 10 years ago, which is your physical machines. You want to leverage the storage affinity, the DAS disks. You want to replicate the storage. You want to use things like Zookeeper, eventual consistency. So the fault tolerance is actually built into the application itself. So applications are designed for the hardware. Now it's the opposite. Now applications can actually carve out, they can give out an ask. So I need CPU, memory, and storage in this fashion. Give me the chunks allocated here, here, and here. Right? So now applications are driving the infrastructure needs. Applications can come in and ask for any setup. So what did we do? As I said, we have a unified platform which has both compute storage and networking. We provide one-click provisioning for any data-heavy applications, SQL, NoSQL, big data, AML. And that's only 20% of what we do. I think, in my opinion, the biggest benefit of Robin is we can provide application agnostic snapshots. Bring in any application, Robin can snapshot. We'll talk about application consistency versus system consistency, but at the storage stack level, we can snapshot any application, be it Hadoop or be it Oracle. We can snapshot it. We can do QoS control. We can do backups. We can do upgrades. And we can migrate to cloud. One platform to do everything. Digging a little bit deeper, how did we build it? So we took Kubernetes as base platform. We have not modified any of the Kubernetes code. And to offset the storage needs, so we built an enterprise-grade storage system with all the feature sets that you expect from any standard array vendors. Snapshots, thin clones, data tiering, migration to cloud, encryption, and compression. On the other side, we have a programmable network stack. What we have realized over like 2 or 3 years is some of the applications need to retain their identity. By identity, I mean the IP addresses, host names, and some configuration aspects of the OS. Docker and Kubernetes are very, very good at managing stateless applications because you just get rid of the machine and bring in a new one, attach the volume, and it runs. Just to give a very, very small example, there are IP addresses embedded in the databases. How do you change it? If the IP address of the container is changing, it is a very, very tough problem to go figure out where the IP address or the host name is embedded in the database or on the disk and change it. So what we have realized is instead of just sticking to one model where the IP address is not fixed, IP addresses come and go or containers come and go, let's have a fixed IP scheming. It's an optional thing. You can select this or that. So we support Calico as well as OVS as network providers. This in itself is not enough because this is just giving the building blocks. You got storage, you got network, and you got compute orchestration. What is missing is application awareness. So because you orchestrate Hadoop in one way versus Oracle. That is why we have Oracle admins and Hadoop admins, I think. So that is where application workflow manager comes in. So this has primitives to manage any kind of application, be it Oracle or Hadoop. This is the block that will allow you to deploy applications, scale, snapshot, clone, or migrate. We are a software-only platform. We run on bare metal, VMs, or any cloud, or the big 3 major clouds. Okay, how did we do it? So there is Kubernetes. We have the scheduler API server on top, and we have kubelets in the bottom. So what Robin does is it will envelop the Kubernetes. On the top, we have a meta scheduler. The reason why we need the meta scheduler is because of all the honeycomb items that you have seen, storage and compute affinity, anti-affinity rules. And when you scale out, you have to adhere to the same principles and all that. So we act as a meta orchestrator, and we direct Kubernetes on where to place stuff, both storage as well as compute. On the bottom, we have CNI, CSI, and CRI, runtime plugin, storage plugin, and network plugins, to offset some of the things that Kubernetes does, and to also provide value add. For example, today we can launch LXC containers and Docker containers in the same application manifest, using the same application manifest. This already covered. One last thing that I'd like to add on this slide is users are not bound to use Robin UI or Robin CLIs. They can use native Kubernetes command set, Helm charts. Anything that is allowed in a native Kubernetes platform will be allowed on Robin platform. You can bring in any new component, just drop it in, and it will work seamlessly with Robin platform. Yeah, go ahead. Inside Kubernetes. Yes.
Those nodes, right? There are two nodes here, right? That was the nodes. The node you present this node running inside what your machine. Or it could be bare metal, could be anything.
Yes, could be anything. Yes.
How do you manage those?
The physical servers. So you're talking about the bare metal of the VM management, right? That's offset. I think that is handled by tools like Terraform and stuff. So where you go and spin up clusters or Nomad.
Majority of people doing it, right?
Yes. So, but
how do you manage those? Who want to manage that? VM die or the whole node die?
Good question. So in the VM dies, there are two questions here. What happens to my application that is running on the VMs, or the containers that are running on the VMs? And what happens to the storage that is attached to the VMs? For example, EC2 instances, EBS blocks are attached. So what Robin will do is Robin will migrate both of them. So it will migrate the containers over from the failed EC2 instance, and it will detach the EBS volumes and attach it in the rest of the node pool.
So you don't need to build a shared storage?
It's a distributed storage stack. We just move the things over.
In the case of public cloud, we consider the case of natural virtualization. How do you do persistent IPs and networking in that case?
So from our experience, I think both AWS, all three clouds treat the networking as different. So in AWS, I think you get a public IP which is not even visible inside, and you get a private IP address.
Yeah.
So let's say you have a private IP address on an EC2 instance, and you're spinning up 4 containers, right? What we do is we actually go and provision out 4 private IP addresses and assign them to the containers, and then we route it out.
Okay. And when you have when I need to spin up a new, okay.
Thanks.
Put an OVS on AWS?
So we have 2 options there. One is you can always choose to go with elastic IPs. Yes. So that is on top of what I just explained. If you want the service to be exposed outside, it's just flip of a switch. Say I need elastic IP, you get an elastic IP.
So anybody who's an old telco hand knows that there was like these OSS systems for operational support, and then there was the business systems, right? So as you're spinning up clusters, somebody's on the hook for maybe $100,000 bill, like at the end of the month, right? So how are you dealing with scoring something so that, like, as you're provisioning it, somebody knows that they're within their limits, within their budget?
Good question. I think Tushar will show that, but we have a concept of tenants, and within a tenant you have users, and you can set limits for tenant as well as users. Let's say I won't allow you to spin up a Cassandra cluster with 60 cores and 1 terabyte of RAM. So a user can be limited to a certain number of resources. So that's all. I think Tushar. Oh, so what is it? Hey.
So I'll go through the demo. So before the demo, has anybody tried deploying Hadoop on Kubernetes? And how was it? Not good? Okay. Now let's see how, I mean, in addition to what, thanks for that. Let's see how the Robin UI looks and how the experience of deploying any application on Robin platform works. So this is Robin. This is currently on premises. It is a 5-node cluster, and you can see the CPU, memory, and everything. So as soon as you add a node to Robin, we will discover the compute available, storage available, and memory, and then we will try to allocate storage and everything from this cluster. So we work on top of Kubernetes, right? Like on GKE, we can go and deploy our software and can work. Or if given a bare metal boxes or just EC2 instances, we will install Kubernetes and we'll start working on that. So even installing Kubernetes, you don't have to worry about. So we have an installer which will run for like 15-20 minutes, which will install Kubernetes along with the Robin stack. And we do not modify Kubernetes. So anyone, we just take a vanilla Kubernetes and add Robin software as daemon sets or stateful sets, whatever is needed. And this is the applications that we support. So it looks like more of a AppStore. We try to give a AppStore experience with single-click deployment of applications, and whatever workflows we provide, we try to have the operation in a single click. So no more than single click for any of our operations. So you can see all the popular Hadoop distributions: Hadoop, MapR, Cloudera, Hortonworks. Everything should be there, and some AI/ML application like TensorFlow, Spark, Splunk, and we also support Oracle and SAP HANA on the platform. Now, just creating the application, you can just click the say this is Cloudera. So you will see different roles that are possible for that Cloudera roles, and we will deploy all these applications. So you see CM server, data node, gateways, and you can control how many data nodes you want. You can try to start small, and you can always scale out as your needs grow. You can specify how much CPU memory you need and all your storage needs. And then on top of that, like Ravi mentioned, that we support compression. Then you can say that my workload is ordinary or latency or throughput or dedicated. So when you say my workload is dedicated, that means we will not create more than one volume on a particular disk. When we say latency, we will not allow more than one latency volume to come on the same disk, so that they won't compete for IOPS. Then you can provide options, Docker options, if you want anything for the image and all the environment variables that you need to pass. And once you do all this, you can select what kind of network you want. You can have different resource pools. So resource pool is essentially a set of machines that you can carve out. Yeah, go ahead.
On the node with the local kit, or is it what like
so we work on top of disk. So we have our own distributed storage. So we take this. So either the disk can be coming from local, it can be coming from SAN, or it can be EBS volume. So, but we format the disk when we try to use it.
So you have your own CSI.
Yes, we have our own CSI. That's right.
And the target is we have the or the USI device. That the one. They go with it. Okay. What you have to use the what you want. Without that, you can go to device to this one. Are you dealing with multitenancy?
Yeah. So in multi-tenancy, you can create a tenant here, and you can define a new tenant, and then you can add users to that, and you can have limits and quotas here. The thing is max application per tenant, max clones, max snapshots, how many applications can you create. or how much storage can you use, memory can you use per user, all those are limits. So say you have a cluster with say 1 terabyte memory. Within that you can say one user cannot take more than 250 GB of memory for their applications, and you can distribute same for storage, yes. Networking, you can have your own IP pools. So one tenant can get the whole IP pool, the other can use different IP pools and so on. Same IP. I mean, so we allocate the IPs, right? So we know what are used, what are not used. Between tenants, no. Within a cluster, you have to have this global. Calico, we add it at the global level. So you can have multiple Calico IP pools with different things, and then it will go.
So IP pools, they will coming with a Kubernetes, or is it a custom?
It's a custom given solution. So we have written our own IPAM, or the IP address management, which will take care of all these IP allocations and releasing and so on. No, it's not open source.
We hook up with the public info blocks, IPAM.
So integration, we have a very open system. We can integrate with newer IPAMs, but today what we have is our own IPAM. Yeah. So Kubernetes namespace, you cannot have nested namespaces, right, in Kubernetes. So you cannot create a tenant and then create within that namespace. You cannot create multiple users so that all of them will be in the same namespace and can see each other or share the same resources, right? So what we do is we have abstraction on top of namespaces. So for what we do is for each user we create a namespace, but then we create a tenant administrator which has access to all these namespaces. So then the administrator can see the whole picture.
So one tenant market is one namespace?
No, one user, one namespace, but the tenant administrator has access to all these namespaces. Yeah.
So for the operators, do you have anything for version management? Because a lot of times you have like a package, you want to roll out the whole thing at one time, you've tested it, you're good on that, and so what do you do for operator version management?
So you mean the application version management, right?
Yeah.
Okay. So what we have is you can have what I showed you, the bundles, right? So bundle is basically one bundle for each version. So you see here Cassandra 3.0 and Cassandra 3.7. So when you deploy the applications, if we see that there are multiple applications, multiple versions of the same application, we detect that, and then you can update the application just from here. So you can decide to go for rolling upgrade if the application supports it, so that we will upgrade one instance at a time, or you can have a test upgrade. What you can do is we have snapshot and cloning capability, right? So what we do is we create a snapshot of the application, create a clone, then you can test your upgrade on the clone, and if you are satisfied that this is what I want, you can go back to your production application and upgrade it.
Okay, so is this defined by you? Is this defined by the user, or is this defined by the database developer?
So this is defined by the bundle writer. So bundle is essentially manifest what you will see in Kubernetes like a spec file, or in the Helm like a chart that you can easily write, and then you can define which bundle can be upgraded from which version and so on. So whoever manages the bundles, that administrator can decide which version can it be upgraded from or upgraded to. So I have, oh, sorry.
Specific to containerized users, you will do name node etching. And secondly, how do you handle the locality? Because that was the biggest issue when you have like a network abstraction layer on top of it. The locality system, especially when you're doing it from Spark and you want to locate your container with data node.
So you want to have it on the same node, as you're saying, right? So let me then just go to the bundle that I was showing, right? So in say I'm trying to deploy Cloudera, and what you said, right? I want data node and Spark on the same node. So let me, Spark may not be here, but let me show you the advanced configuration that we have, right? So you can say that this is data node. What I want is, you can say always place a data node on a node which is also running the name node. I mean, just for the sake of it. If you have a Spark, you can say Spark. Or you can have an anti-affinity which you can say, oh, do not place on a node which is also running, say, HBase master, and so on. Yeah.
It takes a long time. So the can problem is you have two grades. One grade is managing to decide where finishing goes. There is other line which is your story of the script. The pipeline. So it's ordered. You decide where to cover the one not. So the problem is both of them are done. So when you check that box out, they can go into queue. The problem is you plan to figure out what kind of storage is asking for. And if you have an entity set, you take the node with all of these.
So just going ahead with this, so you can say round robin placement of data node across different nodes or across different data centers. So what you want is, you want each data node, say you are deploying on AWS, right? What you want is each data node should go to a different AZ. So you can say, I want in, you can just tag them as a different data center and they will go across different data center. Or you can say, I don't want more than one data center in a rack or a node or a data center, and so on. And as Ravi mentioned, we can have info, storage, and compute to be on the same node, and it is possible due to we plan before we submit our plan to Kubernetes, we plan for compute and storage, and that way we can control where the storage comes from and where the compute will go to. So with that, you can then decide, you can have bigger or smaller of your cluster depending upon the roles you can choose dynamically at the time of configuration. And once you are satisfied with the configuration, what you can do is you can save this as a template so that somebody else can use the same for future. So they don't have to think about all these affinity policies. And also, if you are an administrator who is giving Hadoop as a service, you can define templates like small, medium, large, or gold and silver, and then users can come in and just use those templates to create their clusters. Okay. So, and we also keep track. We monitor what's happening in the cluster. We have integrated. We have the metrics dashboard which will show all this. We have utilization, real-time utilization that you can look at, and it will give you the cluster view as a whole. So I have deployed applications, couple of applications. I have Cassandra, Cloudera, MongoDB, Apache Hadoop, and SDP. And this is just, you can just click on a bundle, click on provision application, and they will be ready within minutes. So look at CDAP. So this is, and then the beauty of this is, these all applications are sitting on your, on those 5 node clusters, and multiple applications running on the same node without competing for resources with each other. And then all the functionality what your Hadoop distribution provides, we don't block it. So it's as good as you can go to Cloudera Manager, and then you can manage your own applications. So you can go to SDFS and everything, whatever is there should work, and it's across applications. So this is CDH, then Hadoop will do the same thing, and so on.
No.
Yeah.
So one thing that we'd like to add is the bundles that Tushar has shown here. These are like Helm charts. So if you have an application, you can build your own application bundle. Again, if your application is data heavy, I think in your case it is, right? So you can follow one of these patterns. The patterns are for building SQL applications like Oracle, which has transaction log or redo logs and data volumes. You pick up a pattern. If you're building a Postgres bundle, it's almost identical to Oracle. Or you have Cassandra, Kafka, they follow one methodology that is masterless. And if you're building something like Hadoop, you pick up. So this is an extensible model where you create a bundle, you write some post rows, And there you go. You can deploy it.
Just scale out at QoS.
Okay, so you have 2 minutes.
Yeah. Okay. All right. Say you are low on resources on data nodes, right? What you need to do is you just want to add more data nodes. So just adding a node is not enough, right? It has to join the cluster and it has to talk to CM server and register itself. So you can just do a scale out. You can say that, okay, I want to do a scale out, how many nodes you want. So it will show estimated usage and all that. You can edit environment variables. You can set configuration options and so on for your new thing. And when this is done, the data node will be added to the cluster without any manual intervention. This is adding new node. If you want to add more resources to existing storage, you can just say, okay, I want, say, more CPU, more memory, and so on. You can just do it, and then it will apply to all your data nodes, and your data nodes will become, will have higher throughput. And then you can control how many IOPS, read IOPS and write IOPS you want to give to a particular role. So that's about from the demo side. So if you have any questions, then we can take it. So our competitors in the orchestration space would be OpenShift and Mesosphere. Yeah. Mesosphere. But where we will shine more is not in stateless application, but more of a stateful application where, since we own our own compute and storage stack, we can control where things go, and we give all this single click functionality and oversimplify things for deploying and managing applications.
Okay. So starting next year in January, we have a free trial version. You can spin up to 5 nodes in any of the clouds or bare metal or VMs, and it is free for life. You can use it. And this is the link. If you want to register, sign up, please do.
Do you have like a back-endless simulation of it so that people could just test out the UI and see what it looks like? Otherwise, we're going to have to put in a lot more than a credit card.
No. So there is one more version that is going to come out where you can run it on your laptop. So it's just a OA or a VMDK file that we ship out, and you can spin it up on your laptop. So any more questions? So currently we are working on cloud migration and test and dev environments where you have an app on-prem. So we can extend the setup to cloud. So you have an application running on-prem and you're running short of resources and you have no plans to grow on-prem data center. So you can just take an application, drag it to cloud of your choice, which is AWS, GCP, or, and you're also providing backups. So the entire application, because of the snapshots, we take a snapshot and we port it to cloud. So you can actually light up your application in cloud. If you have test and lab use cases where you have production database and you want to spin up a test cluster, test application, you can just do it in cloud instead of doing it on-prem. So those are the things that we're working on.